We now discuss the phenomenon of linear thermal expansion. Have you ever found the metal lid on a glass jar too tight to open? One solution is to run hot water over the lid, which loosens it because the metal expands more than the glass does. To varying extents, most materials expand when heated and contract when cooled. The increase in any one dimension of a solid is called linear expansion, linear in the sense that the expansion occurs along a line. Suppose we start with length L0 when the temperature is T0. When the temperature of the rod increases to T0 plus delta T, the length becomes L0 plus delta L, where delta T and delta L are the changes in temperature and length, respectively. Conversely, when the temperature decreases to T0 minus delta T, the length decreases to L0 minus delta L. For modest temperature changes, experiments show that the change in length is directly proportional to the change in temperature. In addition, the change in length is proportional to the initial length of the rod, L0, a fact that can be understood as follows. We start with two identical rods. Each rod has a length L0 and expands by delta L when the temperature increases by delta T. The two heated rods can be combined into a single rod, for which the total expansion is the sum of the expansions of each part, namely delta L plus delta L, which is equal to 2 delta L. Rearranging the pieces, we can clearly see that the amount of expansion doubles if the rod is twice as long to begin with. In other words, the change in length is directly proportional to the original length, L0. We can express the fact that delta L is proportional to both L0 and delta T by using a proportionality constant, alpha, which is called the coefficient of linear expansion. The length L0 of an object changes by an amount delta L when its temperature changes by an amount delta T, as delta L equals alpha times L0 times delta T, where alpha is the coefficient of linear expansion and has the units of inverse Celsius degrees. The coefficients of linear expansion of some common materials are shown in the table. Typical values of alpha are in the range of 10 to the minus 6 inverse Celsius degrees. The forces needed to prevent a solid object from expanding must be strong enough to counteract any change in length that would occur due to a change in temperature. Although the change in temperature may be small, the forces, and hence the thermal stresses, can be enormous. They can in fact lead to serious structural damage. Consider, for instance, a steel beam mounted tightly between two concrete supports. If the temperature of the beam increases, but that of the concrete does not, or if the coefficient of linear expansion of the concrete is smaller than that of the beam, a force will be exerted on the concrete by the beam. Another way to look at it is as follows. If the concrete supports were not there to impede it, the beam would expand by an amount delta L equal to alpha L0 delta T, where alpha is the coefficient of linear expansion of steel. So it is as if the concrete is providing a compressive stress equal to Y delta L divided by L0, where Y is Young's modulus of steel. If we substitute delta L equal to alpha L0 delta T into the stress equation, L0 is eliminated, and we find the thermal stress is equal to Y alpha delta T. Since Young's modulus for steel is 2 times 10 to the 11 Newton per meter squared, and alpha equals 12 times 10 to the minus 6 inverse Celsius degrees, the product, Y times alpha, equals 2.4 times 10 to the 6 newtons per meter squared per Celsius degree, a relatively large value that can lead to enormous stresses. This is why great care must be taken in accounting for thermal expansion when designing buildings and bridges. Next, we talk about an application that takes advantage of the linear thermal expansion of materials. A bimetallic strip is made from two thin strips of metal that have different coefficients of linear expansion, as seen here. The two pieces are welded or riveted together. When the bimetallic strip is heated, the brass, having the larger value of alpha, expands more than the steel. Since the two metals are bonded together, the bimetallic strip bends into an arc, with the longer brass piece having a larger radius than the steel piece. When the strip is cooled, the bimetallic strip bends in the opposite direction. Bimetallic strips are frequently used as adjustable, thermally controlled mechanical switches in electrical appliances. Consider an automatic coffee maker that turns off when the coffee is brewed to the selected strength. While the brewing cycle is on, electricity passes through the heating coil that heats the water. The electricity can flow because the contact mounted on the bimetallic strip touches the contact mounted on the strength adjustment knob, thus providing a continuous path for the electricity. When the bimetallic strip gets hot enough to bend away, the contacts separate. The electricity stops because it no longer has a continuous path along which to flow, and the brewing cycle is shut off. Turning the strength knob adjusts the brewing time by adjusting the distance through which the bimetallic strip must bend for the contact points to separate. Variations of the bimetallic strip are used in old-fashioned thermostats for controlling the temperature in houses and are sometimes calibrated and used as crude thermometers. An interesting example of thermal expansion occurs when there is a hole in a piece of solid material. We know that the material itself expands when heated, but what about the hole? Suppose we approximate a solid square of material by 9 tiles. We can model a hole by removing the center tile. But first, let's see what happens to the individual tiles when we heat up the object with the center tile in place. What happens? It seems like they all expanded by the same amount. Now let's examine the cold object and the hot object side by side. If we remove the center tile of the object when it's hot, it leaves a larger hole than when we remove the center tile when it's cold. In fact, we can move a cold tile into the center of the larger hole in order to see this directly. We could examine many different variations of this demonstration, but they all end with the same result. When an object is made of a single material that expands when heating, the object gets larger, and all of its features, including holes, get larger by the same degree. Or, in specific regard to holes, we find a hole in a piece of solid material expands when heated and contracts when cooled, just as if it were filled with the material that surrounds it. In summary, the length L0 of an object changes by an amount delta L when its temperature changes by an amount delta T, as delta L equals alpha L0 delta T, where alpha is the coefficient of linear expansion. The unit for alpha is inverse Celsius degrees. Next, the linear thermal stress exerted by an expanding material on an object resisting its expansion is given by Y alpha delta T. Finally, a hole in a piece of solid material expands when heated and contracts when cooled, just as if it were filled with the material that surrounds it.